Yeah, so today we'll be talking about Go Stack. I'll start by introducing myself. I'm a software engineer and developer advocate at Dynatrace. My team, and me specifically, work on developing a debugger for production. So that means that for the past 2 years, I've been working on basically building a debugger for Go. It's obviously very similar to the regular Go debugger with a few differences, which have made it much more difficult. I really like the Go community. I'm an organizer of GopherCon and Women Who Go in my country. And other than that, I like sewing, too. Building a debugger isn't really a trivial task. I don't know how many of you have done it. And it's especially not trivial when the way we did it came with a lot of hacks. And so through those hacks, I've learned a lot about the internals of Go, basically reading the runtime code and stuff like that. And I don't know, I thought it would be cool to talk about that, to tell you guys what I've learned, and just dive right in. So what is Stack in general? Stack is a section of memory, right? When our code is running, our app is running, we have all sorts of sections of memory. We have one stack per thread. This is in every program, not specific for Go. And a stack works like a stack, so last in, first out. And it stores things like function parameters, local variables, return addresses, and so on and so forth. Now, if we take, for example, these two functions, the stack is going to look something like this. Once we create the variable a, it's going to be pushed onto the stack. If we call a function, then the function parameters are going to be pushed onto the stack. Once we call that function, the return address, so where we need to return to, will be pushed onto the stack. Then we're going to open a stack frame for that new function. So its local variables are going to be pushed onto the stack, and so on and so forth. When we return from that function, its stack frame is going to be popped, so removed from the stack. And so is its return address and its function parameters. And so it grows and shrinks as we progress through functions. So that's pretty cool. That's the stack in general. Two things to know about the stack. First of all, that it grows down. So it starts with high addresses and ends in low addresses. And we have RSP. It's a register. We can kind of think about it as a variable that holds the last address of the stack. So it's always going to be the lowest address that's currently in use. So for example, here we can see that we have the address is going from highest to lowest. And when we return, then we're going to actually get a higher number that shows a lower stack size. And with RSP, we have it pointing to the last thing we pushed onto the stack. When it's removed, it's going to be pointing to the thing before it. So bigger RSP equals smaller stack. Cool. That's stack in general. Now, the stack in Go isn't the same. And that's what we're here to talk about today. Essentially, it's not the same because threads aren't Go routines, right? Go routines are these lightweight threads. They're somehow magically better and faster. And one of the reasons that they're better and faster is because threads, depending on your operating system, may take between 1 to 10 megabytes per stack. And that's how much they take. It won't be bigger, it won't be smaller. But Go routines start off with 2 kilobyte stack size. So that's much, much smaller. You can create so many more Go routines instead of one thread. That's what makes them lightweight. But what happens if you need more than 2 kilobytes of stack? Because that is small. So Go has this function called moreStack. MoreStack is in Go assembly, so it calls newStack. So I showed newStack here. And newStack will take your existing Go routine, its stack, and it will multiply its size by 2 and give you a new stack and fix everything it needs to fix so that you can use that new stack. Obviously, I'm saying it's all in the Go runtime. You don't need to do anything. And the next question is, when is moreStack called, right? So I have this magical function which creates a stack 2 times the size of the original stack. But how does Go know that I need more stack? So the answer is that the compiler adds a prologue and an epilogue to almost every function. And the prologue will check if more stack is needed. And if so, it'll jump to the epilogue, which will call that more stack function, which will grow the stack and a multiply of 2. So for example, if I wrote the function print3, when it's compiled, it'll look more like this. So while I need more stack, it'll call the runtime function more stack. But needs more stack is just a function that I made up. It's not real. It needs to be a condition that compares the available stack and the stack in use, right? That makes sense. How do I know if I need more stack? If the amount of stack that's in use and the amount of stack that I need don't align. So how does that look like? Well, first of all, we need to know how much stack we have. For that, for every single Go routine the Go runtime creates, it'll hold an instance of the G struct. And the G struct holds tons of things about that Go routine. And the first ones are stack and stack guard. So stack is going to hold the lowest address and the highest address of the stack available to the Go routine. So this isn't necessarily the stack that's in use. It's the stack that can be in use. So for example, if we have this stack available to our Go routine, then our RSP is always going to start at the highest address, so at g.stack.high. And as we add more things onto the stack, RSP is going to move. Stack high, stack low are going to stay the same. So this can move. And eventually, RSP will reach stack low, and then at this point, we'll need more stack. So we can create a condition that looks something like this. If RSP, if the last item we pushed onto the stack is at the lowest address that we can push onto the stack, then we need to call more stack. Pretty straightforward, pretty cool. But more stack itself also needs to use the stack. Just for this example, I wrote 0x10, so 16. It needs more than that, probably. But the exact number doesn't really matter here. So what are our options? The first option is just to have more stack itself have this condition in itself. But pretty quickly, we'll see a problem. So we'll get to the point where we want to call more stack. And then in more stack, we'll still need to call more stack. And in more stack. OK. We see where this is going, right? So that's not a good solution. The second solution could maybe be to just do more stack without calling more stack if more stack is needed. So we'd get to something like this, and we push 2 more values, and we're actually exceeding our stack. We could be overriding values from other stacks, overriding heap, I don't know, overriding things we shouldn't be overriding. So this is not a good solution. The best solution would be to take this into consideration, right? We know that more stack needs, in this case, 16 bytes of stack. We can say, OK, instead of looking at RSP against stack low, we'll look at stack low plus 16 against RSP. Cool, pretty good. When we get to that limit, we'll call more stack, and more stack will push 2 items to the stack, and it'll still be in the available stack space for our Go routine. Cool. This is called stack guard. If you remember the way that the G struct looked, it's under stack. The stack guard is just there to check that we have enough stack, and we don't want to check stack low exactly for this reason. More stack isn't the only function that we do this for. There are other functions which don't have this stack check, or we don't want to call more stack in these functions, so we need to have a certain amount of stack available at all times. It's always going to be between stack low and stack high. So our current condition is if RSP is less or equal to g.stackguard. May look backwards, unintuitive. Again, the reason is that the stack goes from the lowest address to the highest address. I'm sorry, from the highest address to the lowest address, not the other way around. But this is our condition. Pretty good so far, I'd say. You agree? Looking good? Yeah? No? Cool. OK, so we have a nice function that uses, sorry about that, that uses 100 bytes of stack. So once it's compiled, it's going to look something like this. And then let's look at our stack. So let's say that this is our situation. And once we get to this check, then this condition is going to be false, right? Because RSP hasn't reached that stack guard yet. And we aren't going to call more stack. But then once we add 100 bytes to the stack, we're going to exceed it. And once again, we're overriding things we shouldn't be overriding. And the whole point of more stack was to save us from the situation. So we actually did nothing. But don't fret. And I want to take you, before we solve this issue, I want to take you a few steps back to what is stack in general. Because in this case, we know that once we start creating the stack for run first, then we're going to have this on the stack, right? This is what's going to be on the stack, no more, no less, for run first. Now, run first is comparatively a simple function. Let's add a condition to that. For instance, we can have if should run second. And now in this case, still the maximum amount of stack we're going to use is known ahead of time. That's part of the stack being the stack, is that we know the maximum amount of stack that a certain function is going to use at compilation. And we can use that number when checking for if we need more stack. So instead of looking at RSP, we can actually look at RSP plus 100, because we know that this function is going to use 100, or maximum use of stack is going to be 100. And then we can call more stack in this case. Cool. So this is really what happens in Go. I think it's pretty cool. It took me months to figure this out. There's probably some resources, and I also read about it, and I was doing a lot of stuff during that time. But yeah, basically, this is what happens. So if you decompile your Go code, you'll actually see something very similar to this. It does depend on the function you're looking at. If it's a very small function, it might not call more stack at all, because once again, we said there's going to be a specific amount of bytes that's always available for you there. For most functions, it's going to be like this. For bigger functions, it might always call more stack. It really depends. Now, the next question is, how does more stack work? And the thing is that making a stack grow from 2K to 4K, or the next growth after that from 4K to 8K and so on, is not a trivial task. It may sound easy, because we can just allocate another 4K stack, copy the original one to the 4K stack, and that's it, we're done. But it really isn't that trivial. Now, let's look at an example for this. Let's say we have a pretty simple situation here. We have I, which equals 3. And so we push I onto the stack. And then when we want to create a new stack, or create a bigger stack, then we can just copy I to there. Now, what if we have a pointer to I? So let's say I is at the address 1000, and we've got P that's pointing to I. Once we copy that, if we naively copy it, then P is still going to be pointing to 1000. And we didn't leave the previous stack just waiting there, just using up 2 kilobytes of space, just like that. We're probably going to reuse it for something else. And so practically, we've got P that's pointing to invalid memory. So that's not good. We need a smarter way to copy the stack. So a smarter way to copy the stack would be to have P pointing to the new I, right? Yeah, pretty straightforward. But we know this code. We know, we can see it before our eyes. Obviously, during compilation, and later when we're running, we can't see these things, right? If that makes sense. So when we adjust stack pointers, which is the process that I was just talking about, what's going to happen is that the stack pointers themselves must be on the stack. So what that means is that if you have a pointer to something on the stack, that pointer also has to be on the stack. Otherwise, we would have pointers on the heap pointing to the stack, and they could be left dangling. The stack could change. It could move. It could grow. And they would be pointing to invalid memory. The second point here is that stack pointer information is generated during compilation. It's pretty cool, in my opinion. Basically, what happens with Go is that Go generates so much data, or metadata, for every single function you compile. So you're going to have things like this, for example, which is just going to be, I pushed a pointer will be on the stack at offset 5, for example. And then when adjusting pointers, it'll know, OK, the current stack starts at this address. I'll take the offset 5, and there will be a pointer. And so I have to look at that pointer, decide if that pointer is a pointer to the stack or to the heap. because once again, I know the lowest address and the highest address of the stack. If that pointer is indeed pointing to the stack, then I have to adjust it when growing or shrinking. Now, Go generates tons of information. That's not the only thing that it generates. It remembers all your function names, all your file names, line numbers too. Have you ever gotten a stack trace in Go? Probably, right? Yeah. That means that it knows that in your binary is written exactly what line number is associated with the line, with the instruction that crashed. So basically, Go knows a lot about your programs. Now, another thing that may be interesting to look at is what happens when we return a pointer. So for instance, we have this simple function which returns pointer I. And so we'll have I somewhere on the stack. We'll have that pointer to I. And when we return I, then I is going to be popped off the stack. And we're going to be left with that pointer to nothing, to invalid memory once again. Because the next time we run something else, and it's going to push onto the stack in the same place, and then that pointer to I is going to be pointing to something else entirely. So what happens in this case is that a variable is going to escape to the heap. So that means that I is not going to be on the stack. Now, I want to return to that. This is a pretty simple function. Do you agree? I is a simple variable. Like if, I don't know how many, I come from programming in C. I did that for like 4 years, so that's where I'm most comfortable. I'm sorry. But basically, when I see this, I'm like, OK, of course I is going to be on the stack, right? It's going to take up like probably 8 bytes. Pretty simple. When I return from my function, it's not going to be there anymore. I'm not taking up like 8 bytes of memory for the rest of my app until my app dies, just because I created this variable, right? Well, in Go, it's not the same, because pointers in Go are not like pointers in other languages, because Go has a garbage collector. So what's happening here is that we need I to be on the heap. We need I to live beyond the stack of its current function, right? We need that when this function returns, I still exists, so it can't be on the stack. Now, what that means is that I, even though it's really simple, really small, is going to be allocated to the heap. And heap allocation is more expensive than stack allocation. And that's really, really important to know when coding in general, and specifically in Go. Because in Go, well, coding specifically in Go, in general, it might not be true. But in Go, the heap is cleaned by the garbage collector, right? The stack grows and shrinks just by default, by the way it works, like what we saw, like when a new function is called, it's going to create this new stack frame, it's going to push things onto the stack, and once it returns, everything it pushed will be popped. So this memory is pretty much very dynamic, it's fastly changing, things are cleaned automatically, like we don't need to think about it. But on the heap, it's not the same. On the heap, we have the garbage collector, which periodically checks if something needs to be cleaned. And so that check is not as simple as what the stack does. And so just for that reason alone, allocating on the heap is going to be more expensive than allocating on the stack, because things are going to live longer than they need to almost always. Now, the second thing is that the GC will take longer, because the more heap allocations we have, the larger our heap is, the longer the GC will take to make sure the things that are alive stay alive, and the things that can be cleaned are cleaned. OK. Now, a really interesting question is, why do I care? I personally care because this was my job. Like, I needed to know this stuff to do my job well. But I'm guessing a lot of Go programmers don't know this, which is OK, in my opinion. But I think, like, there's a reason I came here to talk about this. And the reason is that, first of all, I believe that you're responsible not just for your code. So sure, you're writing your code, and you are responsible for the bugs in your code. And you aren't, like, 100% responsible for third-party libraries or frameworks or programming languages you use. But when you choose them and when you use them, you need to know how to use them correctly, and you need to make sure that they're working with the things, with the way you chose. So you are responsible for how your code is running, and that does mean that you're responsible for the Go runtime. Now, that is a big responsibility for every single Go developer to hold. But what that means for me is that I like to learn a bit more. Like, that's all. Like, I will never know the whole Go runtime. That doesn't make sense. I don't want to know. Like, sorry. That's really just a lot to know. But I do occasionally try to learn more, and talks like this are what got me to my amount of knowledge today, so I did want to like pass it on. The second thing is that it does help make better decisions. Specifically for this case, or for any case actually, it means that we know what our trade-offs are. Because usually when you're writing a pointer, you think, okay, I want to, maybe, depends, you might be thinking, okay, this is an object that I want to mutate in my function, right? So I want to pass it as a pointer. But in C, for example, a common thought is, this is a really big object. I don't want it to be copied when I pass it to a function, and so I'll pass it by reference, by using a pointer. I came with this kind of mindset when I was coding, when I started in Go. And this is the wrong mindset, and basically just finding this out is what made me realize that it's wrong. Because the more pointers I use, first of all, the more things are going to be allocated on a heap and not on the stack, because they're probably going to be escaped at some point. And the second thing is that when I use there's no need for it. Basically, when coding in C, a million years back, not when I started coding in C, but literally a million years back, memory wasn't as generous as it is today. And so you had to be like, wait, do I really have the, I don't know, 200 bytes I need to copy this again? And then you would say, no, I'll take an 8-byte pointer, a 4-byte pointer, 2-byte pointer, and then use that instead. But when it comes to Go, and usually the things that we're running on, it doesn't really matter. And so using references is usually better. Like, if you need a pointer, use a pointer. But if you don't need a pointer, don't default to it. That's the specific point here. I think the general point is that once you learn how your programming language works, how the things you're using works, you know how to make these smarter decisions and how to be a better developer. Like, once again, you don't need to know the whole runtime to be a good Go developer. I think you can be a great Go developer without, like, your code will look good. It will, like, I don't know, run well. It'll be generic and extensible. But when we're talking about performance, when we're talking about maybe like some low-level issues that occur, knowing how the behind-the-scenes works is very important. Now, the last thing I wanted to mention, back to the technical stuff, is that what goes up must come back down. And for example, if we have this function that keeps allocating, that keeps making the stack grow, okay? We've grown the stack a lot. And then we return from that function. So we don't need this huge stack anymore, and it's just there. So luckily, we have an opposite technique, which causes a stack to shrink. It's from this function shrink stack. It's called by the GC, so it's not like the more stack, which is always called, or always checked to be called. This is called periodically by the GC. And it'll shrink the stack if less than a quarter is being used. Thank you. I did want to say a few more words. Sorry. The first is that I think one of the coolest things about Go is that it's written in Go. And so that's what, like, I know C, but that's what led me to do this. Like, I wouldn't be looking at the code of the runtime if it wasn't the code that I was programming it every single day. And like, at the beginning, I was still like, oh my god, am I looking at the Go runtime right now? Like, what is this the best use of my time? But like, I kind of got used to it, and it's really cool because I've gotten to the point where if I want to know how something works, I feel really, really confident, and I just easily open the code itself, which is really cool. It's usually documented pretty well, too. So that's also a good point to just looking at the code. And the second thing I wanted to say is that Go is a really cool language. It does tons of things behind the scenes. And I think the more we know, the better programmers we are. So thank you.